Okay, welcome all of you. In the previous class, we discussed about bulk magnetization. I said what is a bulk magnetization? This concept is a real concept to understand NMR, because we have to create what is called a coherence. As I told you, we have magnetic moment vectors which are alpha and beta spin states, each of them alpha state and beta states, oriented in the direction to the of the magnetic field, in the direction opposite to that of the magnetic field. We resolve them into three components due to random phase approximation. I said in the xy plane, the components along the xy plane get averaged out. We have only, because of the coaddition, a tiny magnetization which is like a tiny magnet along plus z and minus z. Due to difference in the population, we get a tiny magnet along the z axis, oriented in the direction of the magnetic field, and that is always in the direction of the magnetic field, always stationary, static. For detection of the signal, what we need to do is to perturb the spin system, in the sense from the stationary state we have to create non-equilibrium state. It is in equilibrium, spin systems are in equilibrium. We have to create a non-equilibrium state. That is what we do by applying a radio frequency pulse in a direction perpendicular to the magnetic field. And I said it could be any angle, 90 degree brings it to xy plane, from z axis to x axis or y axis, then 180 takes to minus z, and then 270 and then 360, you can keep rotating like this. And then when you apply radio frequency pulse, bring the magnetization to x axis or y axis, there is an instantaneous phase coherence. This is what we are going to detect, we detect the coherence, and this coherence will not be same in the same phase always. With the time they will start dephasing and it decays. While decaying simultaneously, it grows along z axis. Both are exponential functions. One is a decaying function, other is a growth function. And then we collect the signal decaying along the in the xy plane or x axis or y axis by putting a receiver. This we collect as a function of time. It is called free induction decay, called FID in NMR, common term FID, and this is a time domain signal, and time and frequency are related to each other by a term called mathematical operation called Fourier transformation. This Fourier transformation we do for the time domain signal and get the NMR spectrum, and there will be lots of frequencies present in that. Different peaks are there, each peak corresponds to particular frequency, and as I said, each of these peak is not a delta function, has a natural line width which comes because of uncertainty principle, depends upon the duration for which the spin stays in the excited state. Shorter the time it stays in the excited state, broader is the peak, and this is what I said in the conventionally if you take a proton NMR spectrum of molecules containing NH protons or OH protons, they are generally broad because they are attached to nitrogen and oxygen, which are quadrupolar spins. The quadrupolar spins relaxes faster. As a consequence, they do not stay in the excited state for a longer time. This is what happens, and this is what we understood. And now continuing further, when I say we see the transitions, we see the peaks coming because of the transition between different energy states. But how these transitions are obtained? Is there any rule for it? Let us say if we have different energy states, for spin of one spin we have two energy states. As I go up further, I will tell you, if you have two spin there are more energy states, if you have three there are even more. Then what are these transitions allowed? What are the selection rule? Every molecular spectroscopy we have a selection rule. Similarly, in the NMR spectroscopy also there is what is called a selection rule. And what is the selection rule? Which allows us to detect the signal. The selection rule tells each state or energy level has a characteristic magnetic moment, magnetic quantum number called M, not magnetic moment, magnetic quantum number M, and only the transition in which the magnetic quantum number changes by either +1 or -1 are the allowed transitions in NMR. anything apart from this +1 or -1 are not allowed. You understand? The selection rule is the change in the magnetic quantum number between any two energy states should be either +1 or -1. They are called allowed transitions in NMR. All other transitions apart from +1 or -1 are called forbidden transitions. Okay. Now consider an example of spin half nucleus. Spin half nucleus has only two energy states. I told you that is what we have been discussing. This is beta state, this is alpha state, -half and +half. Now a change of the spin state from alpha to beta or vice versa results in a transition. See what is happening here. Spins from alpha state goes to beta state, spin from beta comes to alpha state. Okay? And this is change here is delta m equal to plus or minus 1. From plus half to minus half, difference is plus 1. From minus half to plus half, difference is minus 1. Both are allowed transitions. So that is why you will get the signal when the spin go from here to here or coming from here to here. Both are allowed. These are all called single quantum transitions. Every peak in NMR pertains to flipping of a particular spin, where change in the magnetic quantum number between two spin states is either +1 or -1. This is the important selection rule condition in NMR. Please remember, every peak in NMR corresponds to flipping of spin from +1 state to -1 state or vice versa. That is why they are called single quantum transitions. Remember, all the NMR spectrum conventionally what you people see, routinely what you take is coming, each peak is coming because of flipping of the spin from where the magnetic quantum number is changing either a plus or -1. They are called single quantum. There is one quantum change of energy. That is why it is called single quantum transitions. Now I will consider the example for a single spin half nucleus in a magnetic field. What will happen? Spin half nucleus, of course, as I already explained to you, there are only two possible spin states. This is the allowed transition. What happens for the nucleus which spin is +1 nuclear spin? For example, some nuclei, deuterium has spin 1. As I told you, for I is equal to 1, m changes from -i to +i in steps of 1. So -1, 0 and +1, 3 possible spin states are there for spin 1 nuclei. This is m equal to -1, equal to m equal to 0 and m equal to +1. Now what are the allowed transitions for the spin? Of course, m is equal to -1 to 0 or vice versa, that is allowed because their change is only 1. Similarly, m equal to 0 to +1, that is also allowed because here also delta m is equal to plus or minus 1 in both the cases. What about transition from this spin to this spin? From m equal to -1 to +1, these are the two energy states. Remember, this delta m equal to -1 to +1 is -2, +1 to -1 is +2. This is double quantum, twice the energy compared to the single quantum. As I told you, they are forbidden transitions, you cannot detect. So this transition is not allowed. From -1 to +1 transition is not allowed. Now let us extend it for the spin 3/2 case. We can consider an example of the nuclear spin which has spin quantum number 3/2. Then what are the possible energy states for this? We have -3/2, -half, +half and +3/2. Same -i to +i in steps of 1 I have taken. Now these are the possible energy states. What are the allowed transitions here? This to this is allowed, -3/2 to -half or -half to -3/2 both are allowed, either it is +1 or -1, there is allowed transition. What about this -half to +half? Of course we saw that in spin half case, that is also allowed. What about +half to 3/2? The difference is -1 and +1, that is also allowed. So there are three possible transitions for a spin 3/2 case. If you consider a single nuclear spin which has three 4 different energy states corresponding to 4 different magnetic quantum numbers, we can expect 3 transitions like this according to selection rule. Okay. So, now we will try to see number of allowed transitions, possible transitions in different coupled spin systems. This is very important, please understand, because we have to use this how to analyze the spectrum as we go ahead. This is in this course we try to analyze lot of proton spectra, NMR spectra of carbon, varieties of nuclei. So, what is important is to understand how this peak comes. The transition comes, any peak in NMR is because of the transition between 2 energy states where delta m is equal to plus or minus 1. Consider an example of CHCl3 chloroform. I have only one proton. I am not worried about these two, I will ignore it, no coupling we will say. Now, if I see proton single isolated spin, what are the possible energy states? Proton spin has spin half. So, it has minus half and plus half 2 energy states. So, there are 2 allowed states possible transitions here, that is plus half to minus half to plus half, both having identical frequency. So, it gives us to single peak. Okay. It gives us a single peak. An isolated spin of nucleus gives a single peak. Always it gives, if you see the chloroform spectrum, CHCl3 proton NMR spectrum, you will always find a single peak, because only one isolated spin, it has only 2 energy states, only one transition is allowed, alpha to beta or beta to alpha, and gives us a single frequency. Now, consider transition to coupled spins. What is a coupled spins? What is a coupling? I will explain that when we go further after 1 or 2 classes. Now, consider situation of 2 spins are there. What are the combinations we can think of? If 2 spins are there, one can be up, other can be down, other also one can be up, other can be down. Now, there are various combinations, both can be up, both can be down, and this up, this down, or this down, this up. 4 possible combinations are there. That is what I have written here, both down, both up, this up, this down, this up. Now, what is the magnetic quantum number of each of these energy states? The magnetic quantum number is just nothing but the sum of the individual magnetic quantum numbers. This is minus half for this spin, minus half for this spin. So, the total magnetic quantum number for this energy state is minus half plus minus half, it is minus 1. Whereas, for this energy state plus half and minus half 0. For this energy state minus half and plus half 0. For about this state both are up plus half, then magnetic quantum number for this energy state is plus 1. So, we know if I have 2 coupled spins, 2 spins are there, 4 different possible orientations are there, 4 energy states are there. Each energy state magnetic quantum number you can work out, which is nothing but sum of the individual magnetic quantum number for each energy state. So, this is minus 1, 0, 0, plus 1. Okay. Now, what are the transitions allowed here? We will apply the selection rule. According to the selection rule, if I write like this, from this to this minus 1, say from minus 1 to 0, it is allowed transition. Okay. Now, one spin can change its state from beta to alpha. In fact, I can find out which spin is changing, whether of the 2 spin, let us I call it as A and X spins, 2 different spins. Now, this corresponds to A transition, because A spin is changing its state from beta to alpha. It is allowed transition, total magnetic quantum number is minus 1 and 0, A transition. Now, what about this one? Here also beta spin is changing to alpha and vice versa, again A spin, this is again 0 to 1, allowed transition, this is also A transition. What about this one? Minus 1 to 0, that is also allowed transition, but notice here X spin is changing its state from alpha to beta and vice versa. Similarly, this is also allowed, plus 1 to 0, again here X spin is changing its state from alpha to beta and vice versa. So, there are 4 transitions and 2 coupled spins, 2 for A and 2 for X. Easily I can identify which are the transitions for each spin, you can identify, you can understand this depending upon which spin is flipping its state from alpha to beta or vice versa. Okay. Now, let us look at energy levels and transitions for 3 coupled spins. It is little tricky, we have to understand this because we will try to analyze spectra of 2 spin, 3 spin, 4 spin, etc. First order analysis, second order analysis, everything we will have to do. But now, what are the possible energy states if I consider 3 coupled spins? Each spin I have identified this as A, M and X, 3 spins. A can have 2 orientations up and down, M can have 2 orientations up and down. Similarly, X can have 2 orientations up and down. These are all alpha states, these are all beta states. So, A can have alpha beta state, M can have alpha and beta, X can also have alpha and beta. Now, all these 3 when they are interacting, when they are coupled with among themselves, now how many energy states you can think of, how many possible orientations you can think of? One possibility, all the 3 can be up, one possibility, all the 3 can be down, that is also possible. Now, we can think of other combinations, 1 up, 2 down, and this are up, this down. So, varieties of combination think of, 2 up, 1 down, and 2 up, 1 down, there are 3 possible combinations. For example, this 2 can be up, this can be down, this and this can be up, this can be down, this can be down, this 2 can be up. So, there are 3 combinations. Similarly, when 2 down and 1 up, again 3 combinations. So, totally if you have 3 coupled spins, if you look at the energy levels, there are 8 possible energy states. This is only one possible energy state where all the 3 are down, minus half, minus half, minus half, all the 3 are down. Total magnetic quantum number for this energy state is minus 3 by 2. What about this? Plus half and plus half, again it is plus 3 by 2. Here is the problem, you look at this energy state, 2 up, 1 down, plus half, minus half, this will become plus half. Same way here, 2 up, 1 down, 2 up, 1 down, all the 3 energy states are plus half energy state. Magnetic quantum number is, for each of these energy state is plus half, total magnetic quantum number. Remember, total quantum number, magnetic quantum number is nothing but the sum of the individual quantum number, okay, for each of these, individual magnetic quantum number of each of these spins you have to consider. Similarly here, now 2 down, 1 up, minus half, plus half, it is minus half. Similarly here, minus half, plus half. So, all the 3 energy state correspond to minus half state, okay. So, there are now 3 possible orientations you can think of, minus 3 by 2, plus 3 by 2 and minus plus half and minus half. Only different 8 energy state, but 4 possible different quantum magnetic quantum numbers are there. Now, what are the allowed transitions here? I can think of the transition from plus 3 by 2 to half. Here look at X spin is changing from alpha to beta or vice versa. That is allowed transition. Plus 3 by 2 to minus plus half is 1. Similarly, half to plus 3 by 2 is minus 1, that is allowed. This is X transition. This is also allowed, half to half. Again X spin is changing its orientation from alpha to beta. This is also allowed. Again X is changing from half to minus half. This is also allowed, minus half to minus 3 by 2. Again X is changing orientation. So, how many transitions we saw for X spin? 4 transitions we saw, okay. All there are 4 X transitions. Now, what about this one? This is allowed. A is changing from beta to alpha. This is allowed, minus 3 by 2 to minus half. You will get half, minus 1. Similarly, if you go from here to here, you will get plus 1, allowed. What about this one? Plus half to plus 3 by 2, where beta is changing again alpha beta A to alpha A is changing, that is also A transition. Again this is the A transition allowed, half to minus half, and another A transition half to minus half allowed. This now 4 A transitions are there. We saw 4x transition, 4 A transitions. Now again this is allowed, where M is changing orientation from beta to alpha. This is allowed, again M is changing orientation from alpha to beta. Again this is M transition and this is M transitions. How many we got? 4 A transitions, 4 M transitions and 4 X transitions. Totally we have got 12 peaks. When 3 protons are coupled, 3 spins are coupled, totally we are going to get 12 transitions, 12 peaks. Remember when we had 2 spins, we got 4 peaks. 2 spins are coupled, we worked out in the previous slide. 4 transitions are there, 2A, 2 for A and 2 for X. Now when 3 are coupled, we get 4 for A, 4 for M and 4 for X. There are totally 12 transitions. You go to the 4 spins, it is even more difficult to understand, because they will have 16 energy states, it is very difficult, but you can work it out. But simple rule is 2 to the power of n transitions are there. If there are n coupled spins, we have 2 to the power of n transitions. If there are n is equal to, let us say 2 squared, there are 4 peaks. Now n is equal to 3. So n is equal to 3, 2 cube, which is 8 peaks. For each of the protons which is coupled, you are going to get, if you look at A will have 4 peaks, M will have 4 peaks and X have 4 peaks. So 2 cube is the energy state totally, and total number of transitions is given by 2nc n minus 1. We will work it out when I come to the next one. When I come to the real quantum mechanical analysis, I am going to explain this to you. So there are 8 energy states, and then total number of transitions is given by 2nc n minus 1. Now flipping of a spin in a coupled spin system, we always saw only one spin is coupled, spinning, one spin is flipping for A, M and X transitions. We got 4 for A, 4 for M and 4 for X. Each time only one spin was changing, state from alpha to beta or vice versa. Now we can think of only these are the possibilities. When a spin is changing from alpha to beta, beta to alpha, whether it is a 2 coupled spin, 3 coupled spins or 10 coupled spin, does not matter. Between 2 energy states, one spin has to change the orientation from alpha to beta or beta to alpha. Then we are going to see the transition. This is where we see the transition. This is the selection rule. Now we can also consider another possibility. It is something different. This is called combination transitions. So far we worked out 4 transitions for A, M and X here. Is there any other thing which we can think of? Look at this possibility. This is half to half allowed. What is happening here? All the 3 spins are changing alpha to beta, beta to alpha. See, beta A is becoming alpha A, alpha M is becoming beta M, alpha X is becoming beta X. There is all are changing, but still the change in the total quantum number is minus half to plus half only. It is still one only allowed, single quantum. See, remember in the previous slide I said only one spin is changing at any time to give a transition, but these are all examples called combination transitions, where multiple spins can flip at a time, but still maintaining the condition, but changing the magnetic quantum number between 2 energy states is either plus 1 or minus 1. These are called combination transitions. Here this is allowed, this is also allowed, this is also allowed. These are the 3 transitions which are allowed. Again all the 3 spins are flipping, but still delta M is always plus 1 or minus 1. So a single spin or multiple spins can flip at any given instant of time, provided the delta M equal to plus or minus 1 is maintained. They are called allowed transitions, and in each of these transition energy change is a single quantum, and that is why they are called single quantum transitions. All the conventional NMR what you people are seeing is called single quantum NMR. That is what I have been telling you. Now let us look at the little bit of details into energy level separation for homo and heteronuclear spins. We saw 4 energy states for 2 coupled spins for homonuclear spins. Now I will see how the energy states, I did not say whether homo or hetero in the previous slide. Now, I will explicitly telling what happens if it is a homonuclear spins, what happens if there are heteronuclear spins. Homonuclear spins means like both protons, both could be fluorine, both could be phosphorus, does not matter. Hetero means one is proton, other may be carbon, nitrogen, phosphorus, fluorine, etc. In these two states, in these two conditions, when you have homonuclear spins or heteronuclear spins, how the energy transition comes, these are the energy states. For homonuclear case, this is the four energy states, but you see this how it comes. Okay. Alpha and beta states are almost nearly equal in both the case. In the homonuclear case, alpha beta and beta alpha states, where magnetic quantum number is 0 for both the states, is nearly same energy. There is small difference, minute difference, do not worry, but we can say practically they are equal. Whereas, if you want to look at the energy state for two heteronuclear spins, it is something funny. Look at it, alpha beta states have substantially different energy. This also m is equal to 0, this also m equal to 0, but nevertheless they are not of the same energy. Energy separation is quite large between alpha beta and beta alpha spin states. This is one alpha beta, and see this is beta beta, this is alpha alpha here, and alpha beta and beta alpha, there is enormous separation. This small energy gap here correspond to dilute spins. For example, carbon 13, nitrogen, etc. They have a low gamma. I told you gamma defines your energy separation. Energy is very small, 4 times smaller gamma. I explained to you in one of the classes previously. Proton energy separation is this much, and carbon has 4 times less gamma, energy separation is 4 times smaller. So, similarly, when you take a heteronuclear spin, this has lower energy separation because of the heteronuclear. These are all larger energy separation because they are other spin, abundant spin like proton or fluorine or phosphorus. This is how the energy states will appear, especially for heteronuclear spin cases. Okay. This large energy gap is for abundant homonuclear spins like proton, fluorine, phosphorus, etc. Okay. So, alpha beta and beta alpha states are substantially different for heteronuclear spin system. But what are the allowed transitions? Again same, there is no difference. This correspond to transition correspond to, let us say, beta to alpha is heteronuclear spin, here beta to alpha heteronuclear spin, here alpha to be, in this case alpha beta for one of them, alpha beta for other one, you can see. See, this is what happens. You can see alpha to beta 2 is changing here, okay, alpha to beta 2 is changing here, beta 1 to alpha here beta 1 to alpha 1, here alpha 1 to beta 1. These transitions correspond to heteronuclear spin, and these larger transitions correspond to homonuclear spins. As a consequence, this peak is 4 times smaller in intensity than this one. If I take this is the carbon 13 intensity is 4 times smaller than proton, because the energy gap is 4 times smaller. This is what little bit of information which I wanted to tell you, especially when you want to understand heteronuclear spin state. So, with this little bit of introduction to NMR spectroscopy concepts, understanding everything we have done. But what I wanted to summarize today is what we discussed in this class. We discussed about the selection rules. Selection rules is the one where the change in the total magnetic quantum number between two energy states either should be +1 or -1. We took the example of spin-off case. In spin-off case, there are two possible orientations, +half and -half, alpha state and beta state. A transition between both of them are allowed, alpha to beta, beta to alpha, because the difference if you take between these two energy states is either +1 or -1. They are allowed transitions. Okay. Whereas, consider the spin 1 case, we have -1, 0 and +1, 3 energy states are there. In 3 energy states, again -1 to 0 is allowed, 0 to +1 is allowed. They are possible transition because the difference is +1 or -1. -1 to +1 is not allowed, it is double quantum, not allowed, that is a forbidden transition. Go to spin 3/2 case, -3/2, -half, +half and +3/2. Now, -half to +3/2 to -half is allowed, minus of plus of is allowed, plus of plus 3 by 2 is allowed. Other things are not allowed because that will be different. These are all single quantum. Anything other than that is different from plus 1 or minus 1. Delta m is not plus or minus 1, it is more than or less than that. They are not allowed. Similarly, we try to understand what happens if you have a combined spin system like coupled spin system like 2 spins. We have possible combinations for 4 different energy state. For n coupled spins we have 2 to the power of n energy states, and 2n minus 2n Cn minus 1 transitions are there, which we discuss later, but energy states are 2 to the power of n. For 2 coupled spins there are 4 energy states, for 3 coupled spins there are 8 energy states. And what are the possible spin states we worked out? For 2 spin alpha beta beta alpha alpha beta 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 alpha beta beta alpha. Similarly, for 3 spins alpha 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 beta 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 and all possible combinations we can work out. There are only 4 possible magnetic quantum numbers for each of them, minus 3 by 2 minus 3 by 2, minus half, plus half and plus 3 by 2 for 3 spins. So, that means what are the allowed transition we can find out. We understood there are 4 allowed transitions for A, 4 for M and 4 for X for 3 coupled space. For 2 spins 2 for A and 2 for X. For 3 coupled spin 4 for A, 4 for M and 4 for X, and each of them change in the spin quantum number is the plus 1 or minus 1. At any given instant of time only one spin is changing its orientation from alpha to beta or beta to alpha. And I also showed you in the 3 coupled case there are possibilities where combination of spins can also flip over. 3 spins from plus alpha to minus half, plus half to minus half could simultaneously switch over, all the 3, that is allowed. All the 3 will change from alpha to beta, beta to alpha. Each spin we are changing either from alpha to beta or beta to alpha, but simultaneously they are flipping, but still maintaining the total change in the magnetic quantum number between energy states is either plus 1 or minus 1. That is, they are called combination transitions, that is also allowed. And then we also saw what is the energy level separation for a homonuclear case and heteronuclear case. In the homonuclear case alpha beta and beta alpha energy states are nearly equal, whereas in the heteronuclear case alpha beta and beta alpha states are substantially different. And for heteronuclear case with gamma is smaller, energy separation is smaller. For homonuclear case, for homonuclear energy states are quite larger. As a consequence, if you consider heteronuclear spin case, energy like a transition of proton is much larger in intensity compared to other heteronuclear spin. For example, if you take proton and carbon, proton intensity if it is quite large, carbon is 4 times smaller than that, 1/4 of that intensity because of gamma. So, this is we can understand this by looking at the level diagram. So, with this I have summarized what we discussed today. So, basically in the last 2-3 classes and till today we discussed lot of things about fundamental concepts of NMR spectroscopy. This conceptual understanding is very important. Okay. So, I discussed a lot of things and explained many things, and in next classes we will start understanding more about NMR parameters like chemical shifts, coupling constants, etc. For till today we have only the basic fundamental concepts of NMR have been discussed, and I am going to stop it here today and we will continue with the remaining topics from next class. Thank you very much.